today's webinar, the Defining Carbon Negative Power Plant Engineering Infrastructure and Storage Considerations. So Kat is going to lead the first part of the presentation.
Thank you, David. So I wanted to go over briefly the objectives of this project. So we worked with CONSOL Energy to help support site selection and CO2 disposition plans for the world's first carbon negative power plant that runs on biomass and coal mine waste fuel. There were various different phases of this project, and during the phases, we performed an iterative LCA to guide their engineering decisions for carbon neutral and potentially carbon negative operation. I'd like to acknowledge a few different people before we move forward with the rest of this presentation. This project was funded through the US DOE and their 21st Century Power Plant program. We have a few different R&D partners that were part of this program. CONSOL Energy was our lead partner. Then we also worked with Worley and Battelle in this program. And then at Carbon Solutions, we have a few different team members that contributed to this project. In terms of some CCS Pro model development applications, we have Richard Middleton, Carl Tosma, Aaron Middleton, and Jonathan Ogland-Hand. And then the lifecycle assessment team has me, Kat Sale, Andrew Harrison, Marcos Miranda, and Tracy Ziv.
Hey, Kat.
Oh, hi, Kevin. There you are. You want to take over?
Well, that was bizarre. It literally cut out as soon as Veronica made the intro there. So sorry about that. Thanks for picking that up, but I am back. So let me see. I think you already went through the intro stuff. So that's good. And at this point, we just wanted to say also that for those of you who are going to be in Houston next week, we will actually be at the CCUS conference there. And we have a couple of papers on this work. So for anybody who wants to take a deeper dive, please come see us there. You can actually get those papers from the URL already. But we will be there next week and would love to meet with anybody who wants to learn more about the work we're presenting today. Let me see if I can actually advance. Okay, so again, apologies. I don't know why it cut out right when we started, but so essentially we got 3 separate presentations for you today, so a little different than the typical monthly webinars. We're going to start out with Kat Sale, who's you've already met. She's going to talk about the iterative lifecycle assessment work, which is really pretty unique for what we've done in this project, integrating with the front-end engineering design. So hopefully that will be of interest to everybody. Then I will come back on and talk a bit about the integrated CCS infrastructure and what it takes to really put these projects together in terms of capture, transport, and storage. And not only for their project, the 21st Century Power Plant project, but also looking at that broader ecosystem of other sources around this region and how their project might fit in with that and get some synergies from that. And then we'll wrap up with some of the cool reservoir engineering work that David Tu's been leading to look at alternative options for carbon storage here. So now turning it back over, as it turns out, to Kat.
I saw a chat comment. Is everybody able to see the presentation, or is anyone else having trouble seeing what's being shared right now? Okay, excellent. All right, so I'll go ahead and get us started then on the life cycle assessment. So I don't know what the range of backgrounds we have on this webinar is. So I wanted to do a brief introduction about what life cycle assessment is before I jump into the grit of what we actually did. So a life cycle assessment is an iterative process to quantify the impacts of a product or a process during its life cycle. And this could be during its conception to how it's disposed of. This could be various different parts of its life cycle. A life cycle analysis is designed to be iterative and interpreted in order to fit whatever goal you have. Life cycle analysis has about 4 distinct parts in order to be ISO 14040 compliant, which we are. The first step is you define your goal and your scope of your life cycle analysis. There are distinct parts to that, and we'll go over that on our next slide. The next step is you collect your inventory. So this is all the data that you need in order to evaluate the impact of your product or process. And then finally, you relate all that data to some sort of impact category so that you can have something that you can compare against. And between each one of those steps, you're going to interpret. You're going to evaluate what you've done and see if you've done it adequately, if there's something that you could do better, if there is design changes that you can do. And I really want to highlight this for this life cycle assessment that we did because we were able to do this step with our with Consol Energy, with our industry partner, which is really unique. And so it allowed us to help them change their actual engineering design in order to make their impact a little bit better. All right, let me take control. So the first step is to define our goal and scope. And so in terms of defining the goal, we have 3 different parts of the goal that we want to look at. The first one is who is our intended audience. So when we were first preparing this, our intended audience was Consol Energy and their stakeholders, but then it was quickly followed by the general public, aka all of you. The category of interest that we were looking at is the 100-year global warming potential. So that means the CO2 equivalent of any greenhouse gases that are emitted or produced during the life cycle of our process/product and how they relate to global warming impact. Then finally, the functional unit that we're going to compare everything by is 1 kilowatt hour of electricity produced. Then you can take these 3 distinct parts and create your goal statement. So for us, our goal was to develop a model of a co-fired biomass, waste coal, and virgin coal power facility that has carbon capture and storage, that evaluates the 100-year global warming potential from generating 1 kilowatt hour of electricity under different system designs for use by Consol Energy. We also wanted to be able to answer this question about what biomass percentage is needed to achieve carbon neutrality at this power plant. The next thing is that we define our scope. What is included in this analysis? So we decided to do a cradle to gate analysis for 1 kilowatt of electricity, which includes the production and transport of any major raw materials included in the process. It includes any on-site emissions. And then we also decided to include the construction of the power plant and any associated infrastructure. Finally, we also included the transport and sequestration of CO2, as it seems to be an integral part for evaluating the actual carbon negativity/neutrality of our plant. One thing we didn't include, which I'll point out, is we didn't include plant decommissioning or demolition after the end of its lifetime. Overall, however, this has been evaluated to have a negligible impact. Next, we used the open source software OpenLCA. We used a impact assessment method from the National Energy and Technology Laboratory called TRACY, which allows you to take various different greenhouse gases and translate them to CO2 equivalent values. Essentially, you figure out how many CO2s a single greenhouse gas is equivalent to based on how much that greenhouse gas, when emitted into the atmosphere, would impact global warming. We have a few different data sources that we used, but we used them in order of a certain priority. The first priority was that if we could get anything from our industry partner, we would use that data first. So there was a feed study done for this work. Thus, we used any kind of data that we could from that. In the absence of data, we use the NETL 45Q LCI and CO2U databases, both of which were generated by NETL to evaluate the life cycle assessment of any kind of DOE mandated life cycle work. And then finally, in the absence of other data, we used values from the Argonne National Laboratory's GREET 2023 life cycle model. All right, so let's get into the nitty and gritty. So once we've evaluated our goal and our scope, we then have to figure out which distinct parts of a process we want to include in our life cycle assessment. And this allows us to look at the plant design a little bit closer. The plant employs 3 different pressurized fluidized bed combustors operated in parallel with a biomass boiler. Pressurized fluidized bed combustor, or PFBC, can generate power in both turbomachinery and conventional steam turbine cycles, like integrated gasification combined cycle designs. It offers higher efficiencies and environmental performance than circulating and bubbling fluidized bed designs. And key, it can allow us to fire waste coal, which is a coal product that generally wouldn't be employed to make power. So we have these 3 PFBCs operating in parallel with a biomass boiler. The biomass boiler also combusts biomass to generate power. And then all of those generate emissions, which then are captured by a CO2 purification and compression system. It's then transported and stored in a nearby saline aquifer. Now, upstream of our actual power plant design, we have a few different things that we evaluated and included in our life cycle assessment. The first one is waste coal beneficiation. So you can see out here that we have waste coal production outside of our system boundary. That's because the waste coal is going to be produced one way or another, whether or not this process is employed. However, waste coal beneficiation would not generally happen, and so we included that within our system boundary, aka any kind of impacts from waste coal beneficiation we evaluated. We also included virgin coal production because a small amount of virgin coal would also be used in this power plant design. And then that's transported to the power plant. The next thing we included was our biomass. So forest residue is collected and brought to the power plant. However, forest management is something that we did not include within the system boundary, since that would occur whether or not this process was employed. Then there's a few other materials that were included in our analysis. Lime, limestone, amine, and PAC were all included with this analysis. All right, so let's move on to the CO2 balance. So once we determined which production processes and were included and how we were going to define all that, then we had to figure out how we were going to interpret the amount of CO2 that was coming out based on how the different parameters linked together. And one thing I like about this is that despite there being so many letters here, I feel like this is actually a very understandable equation. Essentially what we have is all the inputs to our PFBCs and all the inputs to our biomass boilers and how those are translated to CO2. So the PFBC has some sort of inlet air that comes in to allow for combustion, and that inlet air is going to have some amount of CO2. That CO2, when it goes through the combustion process, is going to remain CO2 and be later captured in the system. Some other things that happen is that we have carbon in the coal, and we assumed complete combustion of that carbon, and so it becomes CO2. There's a certain amount of sulfur in the fuel, which is mitigated by limestone that we put in there. So when the limestone, which is calcium carbonate, is combusted, it balances the amount of sulfur in the coal and releases CO2 based on the amount of sulfur in the coal. Then the limestone also has a certain amount of magnesium carbonate in it, and when it's combusted, it also releases CO2. So we have 3 key sources of CO2 in the coal PFBC system. In the biomass boiler system, we again have a certain amount of inlet air that remains as CO2. We also have some carbon in the biomass, which is completely combusted, again, to create CO2. I guess it's not completely combusted because we do have a certain amount of carbon in the ash of the biomass. And that carbon stays as carbon and leaves the system from there. And so once we've tabulated the amount of CO2 that is generated in the PFBCs and the biomass boilers, then we evaluate how much of that is released to the atmosphere and how much is captured. So beta here is our capture rate, and we assumed our capture rate to be 97%. So the remaining 3% is released to the atmosphere. Some of that is from the inlet air, which it's essentially air that comes in and comes out. It's like, we can say that it's not actually generated by our process, so that doesn't count against the process, but some of those CO2 emissions are generated from the process. They're liberated from the combustion of various inputs, and so those do count against the process. And then the remaining CO2 is captured and stored away for the foreseeable future. Some of the model parameters here. I'm not going to go over every single one of these. It would be very boring if I did, but I did want to include these so you can look over them later if you wanted to. But some things, key things to look into is that for the coal plant that we're using, it's 50% virgin and 50% beneficiated waste coal on an energy basis. The biomass type that we're using is 40% is forest residue. And for the baseline process system that we looked at, 20% of the energy that goes into the system is provided by the biomass. Then we have that 97% capture rate. And then we assume that once the CO2 is captured, we need 2 compressors along a 47-mile CO2 pipeline in order to keep the CO2 at the appropriate pressure. And then there's going to be 11 different wells with 1 wellhead compressor that are used to bring the CO2 down into a saline aquifer for storage. The process system that we used to model the CO2 sequestration used a formation leakage assumption of 0.5% CO2. Now, we did want to clarify that this is not an expected leakage amount. In fact, we expect there to be nearly 0, if not 0, CO2 leakage. However, just to be safe and to include this and to evaluate essentially if the CO2 leaked, would there be a problem? We wanted to include that just to be conservative. All right. So what is our output? So the biggest output that we have here is that ultimately our power plant design is carbon negative at negative 57 grams of CO2 equivalent per kilowatt hour produced. And one thing I wanted to point out here is that coal power generally produces 1,000 grams of CO2 equivalent per kilowatt hour. So pretty good. Our big negative amount is coming from the carbon uptake of the biomass that's burned. So essentially you grow biomass, CO2 is absorbed into the biomass as it grows. And then generally for forest residue, right, it would later compost, it would decompose, that CO2 would be released back to the atmosphere. But instead of that CO2 being released to the atmosphere, we're putting it into our system. It is combusting and then that CO2 is being captured. So that's where we get the negative 197 grams of CO2 equivalent here. Some of the biggest impacts to the evaluated life cycle are from the virgin coal. So we assumed that the coal would be mined from an underground mine in Appalachia, and that produces about 67 grams of CO2 equivalent per kilowatt hour. One thing interesting about this process was that we looked at a few different virgin coal emission factors, and we found that there is kind of a wide range of them, but we were able to work with our industry partner in order to narrow down to something that was potentially more real to their system. And it was kind of smack dab in the middle of some of the biggest and the smallest potential impacts of mining coal. The next biggest one or impact is from on-site emissions. So this is from the CO2 that's not captured, essentially that 3% of CO2 that is released. And that generates 36 grams of CO2 equivalent per kilowatt hour, which again, if we look at this, 1,000 grams of CO2 equivalent per kilowatt hour, that is pretty small, which is pretty great. We did a sensitivity analysis to figure out what is that ideal biomass fraction that you need in order to achieve carbon neutrality. And we found that as long as we combusted at least 14% biomass, we could be carbon neutral. Since the plant plans to combust 20% biomass, we are well within that range. One other thing of note here is that the construction and operation of the CO2 pipeline transport storage system has a non-negligible impact on the overall process at about 10% of the overall process impact. We were curious about this, so we actually did a bit of a deep dive and built our own process that modeled the amount of pipeline, the compressors, the electricity required to do that, and the land use impact changes. And that's how we got to our 18.7 grams of CO2 equivalent per kilowatt hour. And in comparison, the kind of pre-packaged solution to evaluating the impact of CO2 pipeline and storage is the NETL CO2U transport and storage process that they generated for OpenLCA, which in this situation evaluated 17.6 grams of CO2 equivalent per kilowatt hour. So we are well within that range, interestingly enough. So we wanted to benchmark this against some other studies. We found that in general, coal without capture, again, is that like about 1,000 grams of CO2 equivalent per kilowatt hour. Coal with 90% capture is about 100. And then one study, Shackle et al., evaluated what it would look like if you used 30% biomass with capture. And they found that their system would be about negative 220 grams of CO2 equivalent per kilowatt hour. Our system at 20% biomass, but a higher rate of capture, is about negative 57 grams of CO2 equivalent per kilowatt hour. I'm showing this just to show that we do benchmark, at least within some bounds here, of reasonable inputs. So, in conclusion, we performed a cradle-to-gate LCA for CONSOL, and we found that the baseline system that they wanted to evaluate has a negative 57 grams of CO2 equivalent per kilowatt hour calculated for the proposed 21 CPB system. We found that 14% biomass must be combusted on an energy basis for the system to reach its expected carbon neutrality goals. And we also determined that integrating LCA into a design process can improve overall system design by identifying key trade-offs and optimizing environmental performance. And how that works is that, we showed them that, yes, you could use a certain amount of virgin coal if you wanted to, that you did have to raise the amount of biomass in order to be able to do that. We evaluated a few different system designs. We evaluated a PFBC that also had biomass in it. And we helped them determine, does this matter? Does that not matter? Throughout the whole process. And we're able to land on this final design. So I'll go ahead and hand it over to our next presenter. I think it's Kevin going next.
Yeah, thank you, Kat. That was great. I love your explanation of how we're tracking every molecule of CO2 through the system and the carbon as well. So it's fantastic. Let me see if I got control here. Okay, so next part, now we're going to look at the broader system. So Kat's talking about really the power plant primarily, and then some of the life cycle aspects of that broader system. What I'm going to get into here for a few slides is this CO2 disposition plan. So apologies again, I don't know why it glitched out right at the beginning, but those two main objectives that we have, the first one was CONSOL came to us at Carbon Solutions because we have these unique software tools to help them work on this CO2 disposition plan, or that is, how would they actually not just capture at the plant, but transport and store that CO2 in the most optimal fashion or least cost fashion. And secondly, how would their project fit into this broader ecosystem? As I mentioned, for those of you that have been in the Pittsburgh area, there's a lot of industry around there, power plants and other things. And just like CONSOL Energy, they're also interested in looking at CCS to mitigate their emissions. So we are able to explore all of this with the unique software tools we have here at Carbon Solutions. The main one being SimCCS Pro, which is really the big optimization software that looks at all that capture, transport, and storage and puts it all together in a optimization so that we can find these least cost solutions for integrating that entire project. In order to do that, we have to have different software and modules that can actually handle the capture piece, the transport piece, and the storage piece separately. And you see those here on the figure with Concord, CostMap, and Scott Pro. So I'm now going to step through some of the results we got using our software for this project. The first one is on the capture side. So you can see here kind of our study area and where we're at. This is the tri-state area there. Sorry, we don't have this now. So this is Pennsylvania, West Virginia, Ohio. So the plant, obviously has not been built yet. and they're looking to site it, somewhere in this kind of area that you can see here. And obviously, using our Concord database, we are able to look at all these different potential sources around them that could ultimately be, in some ways, partners to help them share with infrastructure costs and such to do a broader CCS and carbon mitigation approach for the entire region. So we're able to use that and start looking at those. And then a little bit more in detail, what we can do with the Concord software is breaking down much more than what is typically done with the sort of EPA database on, plant greenhouse gas emissions, where we break it down by the individual emission streams within those plants. So, at a cement plant or say an ethanol plant, you all are probably familiar with the ADM project and storage in the Mount Simon over in Illinois, which is kind of my backyard. They're capturing off of the ethanol fermentation that emission stream. And that's because that's a 99% pure CO2 emission stream, very, very cheap to capture. But associated with that plant, there's also gas turbines and other emission streams. And so what we're able to do with our software is break out all of those things. And you can see on the left-hand side, a range of cost estimates for capturing from all of these different types of emission streams. And so it's not as simple as just saying, hey, there's a cement plant here or a coal-fired power plant there. It's $60 per ton to capture. We really get into the details and try to understand what is the capturable CO2 and what are the costs of capturing from these various emission streams, because ultimately that's what we need to feed back in to do the SimCCS optimization, which is all based on least costs. Then the next part is the transport and storage here. So on the left-hand side, we use this cost map software to actually look at not just your plant, which is shown here. The red dot would be one of the locations that this 21 CPP plant could be located. But how does it work within this ecosystem of other potential capture plants around here? So all the other orange dots that you see on the figure on the left, and then potential sink locations are the green dots. And what the cost map does is actually route all the different pipeline routes and finds the optimal routes there. So again, we mentioned this, the Pittsburgh area, you can see all that bright yellow stuff. That's the really high cost of transport. And basically, you don't want to run CO2 pipelines right through the city of Pittsburgh. So our model will actually avoid all of that stuff and find this least cost route for the pipelines. Then on the right-hand side, I'm showing a couple of the solutions coming out of SimCCS. So here the red dots are not just 21 CPP, but how it might actually join in a network with other potential sources, as I mentioned. The blue dot is, or little pie chart is showing, storage at a particular sink there. And then the purple are basically candidate pipeline routes of how that system could optimally come together to transport and store whatever CO2 targets you're looking at. And then the green ones are the actual solutions we get out of SimCCS. It says, hey, out of all these combinations, this is the design you want to go forward and build. And so it's very powerful for looking at all kinds of scenarios. I'm showing you a couple here. And the end result of the analysis we did for the project in terms of SimCCS and transport was we found that there's clearly opportunity to reduce the overall transport cost by 50% or perhaps even more, depending on what kind of scenario might happen. Basically, by sharing that pipeline infrastructure and the investments, not just with our partner, but with these other partners in the region. Then the last piece of capturing, transporting, and storing to get to carbon negative, you got to be able to store those emissions. And so we use the Scott Pro software, and we've used this in on formations across basins all across the U.S. and even some internationally as well. The figure I'm showing here on the left is our cost estimates. So if anybody's interested in this Scott Pro stuff, we have a lot of publications. There's another webinar that Jonathan Oglen-Hand had already done on this. I believe, in our archive. So there's a lot of information on how we do this, but basically we try to look at estimating what storage costs would be in deep saline formations. And you can see on the left-hand side that overall Appalachia Basin, we find has relatively high storage costs, we think, for saline basins. There's a lot of uncertainty in these data because we typically don't have a well right there and detailed characterization, the kind of things that you would do to get to a Class 6 permit. We're not at that level here with this study, but in general, what we find is you're looking at probably $15, $20 per ton, all the way up in the greens are 40 and the reds are, $60, $70 per ton of storage. So that's relatively much higher than what we see in places like the Mount Simon in the Illinois Basin and such. And, that's a little different than what was reported in NatCarb and the carbon storage atlases of past. Many of us worked on those projects with volumetric estimates. I was at Indiana Survey and we know the Pennsylvania folks and everybody worked on these things. These storage resources look promising from that kind of general regional perspective. But as we tunneled in here, and you can see on the right, even though we don't have a test well for this particular project, we looked at data from the other wells, and you can see all those squiggly lines. Those are borehole geophysical logs, and we use that to look at, what is the reservoir characteristic of these rocks. And so even though there's a lot of good looking targets and a lot of formations that we think are probably, reasonable targets for CO2 storage in Appalachia, we find that most of them are pretty tight, and it's just these thinner intervals without there. You can see where the squiggly lines deviate quite a bit, like up in here and stuff. So that's what led us to basically find, much lower kind of storage capacity than what those earlier regional characterizations came up with, and lower injectivity overall. And so that's effectively what drives up the cost for, we believe, CO2 storage here in terms of deep saline formations. So how this all comes together then, again, out of SimCCS, we can look at the whole integrated system and come up with estimated revenues for what your project will look like. And what you can see here in the graph is, a 20-year project period. And what we estimate are the overall revenues that could be achieved when you consider the 45Q tax credit, in this case for $85 per ton of CO2 for saline storage, and you subtract out all the cost of capture, transport, and storage. What I'm showing here is a range of expected revenues for the project. And you can see through these first 12 years, it could be anywhere we expect from, very little revenue all the way up to $1 billion of revenue over 12 years. And that sounds pretty fantastic, but when you take $85 per ton and you're looking at, in this case, 3 million tons per year, you can generate potentially a lot of revenue if you have the right storage resources and if your capture costs aren't too bad. So the uncertainty you see in this is based on the storage part. And so, this is kind of pretty amazing to get up to $1 billion, but we're also saying, given that uncertainty here for saline storage, if you get down in here, this would be very marginal. There's a potential that you're not going to make money. So these are the kind of things, and obviously the next steps, if the project goes forward and wants to look at, they've really got to, drill a test well and kind of get a better handle on the saline storage options. The reason this thing dives down after 12 years is because the current tax code only allows you to get that $85 per ton credit through 45Q section for 12 years. So that's what the overall revenue forecast look like here. And because of this big uncertainty in, what the saline storage might look like and how that impacts the economics of the project overall, we turn to this alternative storage option, which is, the potential in this region. And you can see the figure on the right-hand side from the Penn State group. This is showing the number of wells drilled in the Marcellus from the early exploration, 2004 all the way up through, in this case, about 2020. And so there are literally thousands and thousands of Marcellus wells that have been drilled here. And a lot of prior work suggests that, there could be gigatons of storage in those Marcellus wells, the depleted wells, that is after they've produced for, 10 years or so. They typically have pretty steep declines after the first few years. And so the idea is we could convert some of those existing well infrastructure into CO2 injectors. And this is an attractive idea, not only because folks have estimated, there's quite a bit of potential storage in this reservoir, but also because we expect the overall cost to be cheaper. You have existing well infrastructure, you have the existing fracked reservoirs at reduced pressure. There's already pipeline rights of way in place. There's storage security from absorption. So that's another key piece. In saline storage, you're injecting the CO2, and then you have a separate phase plume that's mobile and, transporting through the reservoir. Whereas here, you're going to get basically instantaneous absorption for a lot of that CO2. So the storage security is a big deal and is advantageous for this. And that also leads to a smaller AOR for monitoring. So overall, many of us have been working on this concept for many years. And basically, we're thinking that, wells that have had roughly 10 years of production or so history, even though many of those are still producing, kind of trickling out some gas, and they're still economic that way, what we're seeing is that they're probably more valuable for conversion to CO2 injection than the revenues they're getting from continued production. And so that sums up the last part of our webinar, which is a really deep dive into this concept based on reservoir engineering. And now I'll turn it over to David too to present that part.
Thank you, Kevin. So good morning, everyone, again. I'm David Tu, the reservoir research scientist at Carbon Solutions. So also based on the broad background of the audience, potential backgrounds of the audiences, that I'm just going to briefly introduce what the reservoir simulation is and what the numerical modeling is. So then numerical modeling and reservoir simulation is the tool that to access the planning, monitoring, and evaluate the commercial scale CCS projects. So it is powerful, but doing the analysis in a digital way for creating a digital twin of the reservoir model. So the numerical modeling will be creating the model that represents the site geology, rock and flues properties, as well as the injection wells that you plan to place in the area of your study. So after a workable numerical model was constructed, then we can play on the reservoir simulation to discuss and investigate different scenarios, strategies of this injection or production in the area to make it a optimal development plan. So I do want to highlight on what's the difference of the Scout Pro tool versus the numerical modeling and the reservoir simulation. So our Scout Pro tool is a powerful tool that to quickly estimate the ultimate volume that an area or a reservoir that can store, and it answers to the question of how much can the reservoir host ultimately in let's say the hundreds of years. But for the numerical modeling and reservoir simulation, it computes the rates of injection. It answers the question of how fast or in a certain period of time that the CO2 can be placed in, and also monitoring how the CO2 plume is going to develop after in undergrounds after the CO2 was injected. So just quickly, why this study is necessary, because at first it enhances the confidence of the storage scenarios, because it is a millions, billions of dollars investment. So we do want to have a high level of confidence before we actually study the construction, and also drilling the storage walls and also the reservoirs that to be used at the host reservoir. And also for the reservoir simulation that we can create unlimited scenarios to really develop a plan that tailors optimize the company's financial capability and the outlook. And eventually, it is also meets their regulatory requirements. So just to give you a brief look on what the requirements are, that the computational modeling for geological storage provide the necessary background of the owner operators. It's actually required by the Class 6 rule that by EPA as well as the federal codes that it requires that when we put in a Class 6 permit for the injector that we need to provide the area of review, which are the impacts of the expected impacted areas of due to the CO2 injection. So without the reservoir simulations that a Class 6 permits, it is impossible to be granted. So next, I'm going to dive into this specific study. So this study is the final component of the source to sink streamline analysis that Carbon Solutions is capable of performing, which is the subsurface sequestration. As Kevin has said, that the specialty of this study is that we're not looking into the saline reservoir. Instead of that, we're looking into the depleted and oil and gas, or more specifically, the Marcellus Shale reservoirs as an alternative storage plan. So in this study that we picked the well cluster that's called the Ridge Road Horizontal Well Cluster. The cluster of the well is located in the southwest of the Pennsylvania states, that's close to the borderline, and also that's close to the potential source that Kevin just showed us. So there were 8 branches in this well clusters. They are all horizontal well with multi-stage hydraulic fractures. They are all natural gas producing wells. If you see the well status here, that 4 of those wells, 6 of those wells are actively producing, while 2 of them are inactive. So in the study, we picked the northwest 4 branches of the well cluster as our study objects because if you see the figure here, this one shows the cumulative natural gas production from those 8 wells. We can see that the southeast 4 branches of the wells that they started producing not until close to 2018, but the other 4 wells that started producing between 2014 and 2015. So they should be treated as 2 different groups, and also based on our analysis that the impacts from the orientation of the branches on the southern side doesn't really impact what happens in the northern side. So that's why that we built our model that just surrounding enclosed only these 4 branches. The other reason for that is that you can see that for Ridge Road number 5 and 6, those 2 inactive wells, that they stopped producing at a year of 2017. For that reason, it gives us more room to create different analysis in terms of when are we supposed to convert a methane producer into a CO2 injector. That gives us more scenarios to optimize. So here's some parameters that the model set up. So for the dimension of the model, it just ranges, it is a rectangular that basically encompasses the lateral length of the wellbore and also the dimensions of the 4 branches. So the area that encompasses the total number of grades, it's close to, it's more than 500,000, and each grade, the size is 50 by 50 feet. And the average thickness of the area of the Marcellus Shale is 177 feet. And the porosity and permeability were acquired from the previous study performed by MSeal. The MCO represents the Marcellus Shale Energy and Environmental Laboratory, that they have performed a comprehensive analysis in terms of the petrophysical properties of the reservoir. So we utilize those numbers. Also later on that we have verified how accurate our models performs with these numbers being added. So for the initial condition of the reservoir, that we assume it is the 100% saturated with methane with a quarter of irreducible water saturation, and the reservoir pressures were all initialized by the previous study. So on this chart, you can see that the first step of our study is to match the historical methane production. So Kevin mentioned that for a shale gas horizontal well, its lifetime is about, for the first 10 years, the production from each wellbore will drastically decline from to 20% of its original of this initial production rate. So that means that there should be an optimal point for where from the finance perspective, there's the balance point where you want to convert your producer into injector to take the benefits, the 45Q credits, to maximize the revenue. So this chart shows the historical production of these 4 wellbores that I mentioned before. You can see that these 2 wells stopped producing at a certain time, and the rest of the 2 wells were just keep producing until the end of 2025, which is the latest data that we can acquire. So according to the history match, these circles are the field data that reported to the states, and these dashed lines are the results produced by our simulations. We can see that we achieved a reasonable match for the historic reduction, which means the initial inputs parameters that we showed in the previous slides are valid. After that, this is a scenario where you can see in these yellow blocks means the years where the wells were producing methane, and these grayed out blocks were where the wells were inactive. So we first simulated the history production, and then these green blocks that represents the active CO2 injection. So in this scenario, that's all 4 wells were converted into a CO2 injector at the year of 2025 and started injecting for 30 years forward. You can see that from here, this dashed line that you should read from the red chart or red axis that represents the cumulative mass of the CO2 being injected. You can see that these 2 wells, which were previously terminated from the production, yield the lowest storage volume, while the other 2 were basically yield the maximum of CO2 injection. This could be due to the fracture properties, the reservoir properties of those 2 branches, but also it means that it could mean that there were some correlations of how much the CO2 that it can inject is correlated to the methane that was previously produced, that to make the reservoir pressure lower as well as the pore space available. So in here that we summarize the injection and the static parameters that we put in for these 4 horizontal wells. Now you can see that on the x-axis shows that the total CO2 more being injected, and the y-axis represents the different parameters that shows on the top of this chart. So we can see that the total stimulated reservoir volume is the big factor of how much CO2 can be stored, which is not surprising. That basically means that network, the channel, with considering the frac stage, the frac density, and the lateral length, as well as the frac width. So the other components that we noticed that is the prominently proportional to the total amount of CO2 can be stored in these type of shale reservoirs, how much the CO2 methane were previously produced. Like I said earlier, that more methane produced means the pore volume became more available, as well as the reservoir pressure. to validate that idea, on this slide, you can see that we performed another simulation that where we just let the ridge road number 7, number 1 just keep producing throughout the whole, let's say, 60 years, and only converts the well number 5 and number 6 at the year of 2025 to inject for 30 years. Now we can see that compared to this dashed line where all wells were converted to injectors, we can see the average reservoir pressure, this red line, represents were much higher compared to this case where only 2 wells being converted, and as well as the total storage of the well number 5 and 6 in this scenario where the solid line represents were much higher than where the reservoir pressures were also much higher. So that gives this idea that with the strategically planning on the timing of converting those horizontal wells, as well as the let's say the pattern, the conversion that can highly impact the total CO2 storage in this in these shale reservoirs. So here's the last slide that I'm just going to show you a quick animation of how the CO2 plume is going to respond. You can see these 2 wells were the producers just to keep producing well number 1 and number 7. And the color represents the CO2 saturations that you can see as the CO2 started to injecting in these 2 wells, because the pressure drops were much higher in this region that we're seeing some CO2 were capable of penetrate through into a deeper of a reservoir matrix instead of just to stay at the stimulated reservoir area, like this well. In this adjacent well, it actually allows the CO2 to penetrate through into a deeper spaces. So, excuse me, to conclude that the CCS in Marcellus Shale formation through depleted modest stage fracture horizontal well shows the potential of the mega scale CO2 storage in the cluster pattern. The model simulation indicates that at least a half a MGTOW per well, with this more than 3 million tons of CO2 being stored in this half cluster, or the half of the pad area. And the major CO2 storage may be achieved by the early stage injection, and the strategic planning can of converting those natural gases in terms of pattern and timing can be optimized for a maximize the financial gain, and in terms of the revenue and also the total CO2 being stored. And with that, I've concluded this part of the study, and I'll hand it back to Kevin to summarize this webinar.
All right, David, thanks. You know, the result of this more detailed analysis is we had estimates of these big Marcellus producers, 8, 9, 10 BCF production would come in around 1 million tons or so of CO2 storage. And what we've learned with the work with David is that, you know, it's much more complex. It depends on this history of the other wells around you, how depleted the reservoir gets to. So a more general rule of thumb we would be using right now is more like around 500,000 tons per well, which ends up for that cluster being, you know, 3 to 4 million tons of storage just for that well pad cluster. So I think ultimately this is still a real opportunity that needs to be looked at, particularly as we mentioned that saline storage looks to be a bit challenging. So that's the conclusion on the third one. These things were summed up in each piece, so we're about out of time. So I think we should just open it up to a few questions. And again, you know, reach out to us anytime if you want to hear more. And obviously, we hope to see you next week in Houston as well to talk about more of these details.
Kevin, Kat, thank you all so much. I am going to be dropping a link to subscribe to our newsletter where we update our webinars each month for those of you that might need to get going here. And any of you that might have questions, please feel free to drop them in the Q&A. David, right now we do have a question in there for you from Douglas. David, how does your pore throat pressure affect your models?
This is a good question. In the pore throat fracture, let me say, sorry, let me just open the chat. Let me have a closer look. Is the question in the chat? I'm sorry. Veronica?
It is in the Q&A. I can go ahead and move it over into the chat for you, David.
But in general, the pore throat ratio that it impacts the entry pressure, which is the part of the capillary pressures. But in this simulation model, the reservoir simulation model doesn't really consider that, because usually we set the capillary pressure to the cap rock, which usually to be the shell. But the special of this case is that the shell itself is also the hosting reservoir. So I forgot what the exact question is, but in general, this study doesn't consider the pore throat ratio.
Thank you, David. And we have one more here in the chat as of now. Big picture, I love the storage and shales. Are you concerned about Class B approval for that / any thoughts on what that would require?
I'll take that one. Did it say, I can't see it, did it say class 6 approval? Is that what they were asking?
Yep, a Class 6 well.
Yeah, I mean, so there's a lot of questions here. It's could they actually be permitted under Class 2 as kind of an EGR operation or enhanced gas recovery, like we have CO2 injectors under enhanced oil recovery? To get the credit, do they need to be in, would that be the $60 credit instead of $85 credit? I mean, these are all questions that haven't been answered yet. So there's a lot of open questions. So on the permitting side, I think that's one of them. Right now, from our perspective, we're just trying to get a better handle on what the technical potential is, and then how that relates to the economic and the production history. And again, many of us have thought about this for many years and worked on it in various ways, but I think the work that we're doing now is really starting to hone in on kind of the ballpark of what this might look like. And so from our perspective, if this work says this is really a viable option, then you need to be looking at all the other pieces such as permitting to really make this happen.
Thank you, Kevin. The next one in the Q&A is, does the model include absorption?
Yes, it does. It includes the competitive absorption between the CO2 and the methane. So yeah, it wasn't showed in this slide deck, but I believe it is covered in the CCUS paper or the abstract that has been published online. So if you're interested, you can see that. We do see that the competitive absorption plays in a big role in terms of enhancing even more methane being released that potentially can be produced for extra revenue as well, CO2 being absorbed and sequestered, stored.
Thank you, David. And it looks like the last one in the Q&A here for now. Have you looked into the remediation costs for abandoned wells?
In the case of what we're looking at here, they would not actually be plugged and abandoned yet. For the most part, we're thinking about ones that haven't gotten there yet. But the big cost, I mentioned all these advantages of maybe this relative to saline storage. Big one being this infrastructure in place, but you certainly have to do a workover on these wells to put in stainless steel or chrome tubing, because converting to CO2 is very corrosive. And so, there's still work to be done there. So there's certainly costs but they're not really plugged in abandoned wells yet, but you can think of it that way.
Thank you, Kevin. I'll leave the Q&A open for another 30 seconds here or so, in case anybody has additional questions for the group. But again, I'd like to thank you all for joining us today. We do try and host a webinar on the 4th Wednesday of each month. So again, please reference that subscription link in the chat should you choose to follow our newsletter. Kevin, Kat, and David, unless you all have final remarks, I will get ready to close out the meeting for us today.
Sounds good. Thank you, Veronica.
Thank you all.